Bonjour, donc voilà, bienvenue pour le séminaire de Daniel Suchet. Donc on va attendre un petit peu parce qu'il y a plusieurs réunions là, en ce moment, donc on va attendre que ça se remplisse un tout petit peu. Et puis on va commencer, donc je peux pendant ce temps-là faire une toute petite introduction pour Daniel. Donc comme vous le savez, on a décidé de faire à peu près une fois par mois, tout ça, des séminaires qui sont plus basés sur l'énergie, parce qu'une des questions très fréquentes après nos séminaires, quelle que soit à peu près la discipline des séminaristes du LSCE qui donnent des séminaires à l'extérieur, c'est bon, très bien, qu'est-ce qu'il faut faire maintenant? Il y a beaucoup de questions sur la trajectoire énergétique, les possibilités énergétiques, et on s'est dit avec le groupe des séminaires que ça valait le coup d'inviter des gens sur ces thématiques précises. Et donc à peu près une fois par mois, on aura une thématique sur ce type euh, de problème. Donc c'est avec plaisir qu'on reçoit aujourd'hui Daniel, qui est en fait un voisin puisqu'il travaille à l'X. Et Daniel, j'ai eu l'occasion de l'entendre plusieurs fois, est un très bon vulgarisateur. Il explique les choses très simplement, il a un peu un don pour ça. Et là, aujourd'hui, il va nous parler du solaire, de l'énergie solaire, de ce qu'on peut en attendre, en particulier du photovoltaïque. Voilà, je pense que tu peux commencer doucement, Daniel. Il y a encore des
Ok.
gens qui vont arriver dans les minutes qui viennent, mais tu peux commencer, je pense, ton introduction tout de suite. Merci beaucoup. À tout à l'heure
Marche.
pour la question. Donc, Nada va prendre la parole pour vous expliquer comment ça se passera pour les questions. Merci beaucoup. À tout à l'heure.
Oui, donc au moment des questions, vous pouvez soit signaler dans le chat que vous avez une question ou la poser carrément. Et puis moi, je ferai la modératrice et j'annoncerai, enfin, j'enlèverai le mute de vos micros, comme ça vous pourrez poser vos questions les uns après les autres. Voilà, bon séminaire.
Merci.
Merci beaucoup pour l'introduction. Merci beaucoup pour l'invitation. Je suis très heureux de pouvoir venir vous parler, même à distance. Et on avait dit peut-être qu'on faisait les choses en anglais pour que ce soit accessible
Ah,
plus.
mince. Yes, I'm sorry. I'm sorry. I should have talked in English all the introduction. I'm sorry that I asked Daniel to do it in English. Yeah, ouais, t'as raison.
So maybe I will switch to English from there on and for the rest of the presentation. So good morning, everybody. I'm Daniel Suchet. I'm maître de conférence. Never found a good English translation for this one. At École Polytechnique, and my research is IPVF, which is the Institut Photovoltaïque d'Île-de-France, which is indeed a neighboring institute just at the borders of École Polytechnique. And IPVF is an institute for the energy transition, ITE, which gathers both academic and industrial partners aiming for solar energy. And we have a research program centrally organized around 6 main axes, ranging from technical, economical analysis of the markets to advanced concepts and theoretical studies, and with, of course, technological programs aiming at producing cells for the industry and characterizing and modeling cells to understand what's really going on. If you're interested in visiting us, if you want to hear more about IPVF, it's really easy to organize things. Don't hesitate to reach for us, and we can organize a lab visit if it can interest you. What I will be presenting you today in the next 45 or 50 minutes or so is to try and give you an overview of the current states of solar photovoltaics. And I'm a physicist myself. My specialty is the basic understanding of energy conversion. So I will start by trying and give you orders of magnitudes, basic working principles, so that you have some notions of what is happening inside the solar cell and what are the basic limitations and abilities. The next thing I'll try and show you is the state of the art of the PV sector today. And what I will emphasize is how things tend to move quickly in this field. And this figure, I think, is quite interesting. It is the comparison between the predictions from the World Energy Outlook of the International Energy Agency and the actual increase of installed capacities in solar photovoltaics. So what you see is that every year the IEA thought that solar would stick where it is of additional capacities, and every year until at least 2018, it happened that installed capacity actually increased from year to year. And to me, this graph really shows how the field moves quickly, how this quick motion might be difficult to capture. And the aim of this presentation for me really is to give you motions of where the field is currently, so that you can draw your own conclusions from there. And finally, I will end presenting you 4 challenges. It's clear that solar is the end of the road yet. There are still many things to do. Many things have been done already. And I will show you what I understand as being currently the challenges which have to be faced. This is the point where I will mention grid integration, and I will mention it briefly because I think we cannot make a presentation on solar without mentioning grid. But at the same time, this presentation is not dedicated to grid integration. It is really dedicated to solar technologies, and so grid will be restricted to a short mention in this. So let me start with magnitudes and basic concepts for solar photovoltaics. Why do we care about solar? I think this picture here is quite striking when you try to picture the different ways to produce energies and the different reserves and potentials for the different kind of energies, and you put together what is actually being consumed as primary energy in the world over a year. You put together gas, oil, coal, and of course we can discuss how these things are actually being estimated, what should be the error bars on these cubes. But what is crystal clear is that solar energy represents way more than all this. And there again, we can discuss about the actual numbers, but the typical order of magnitude is that the solar resource is about 10,000 times the actual primary energy consumptions in the world. If I try to put figures on this, I guess the orders of magnitudes to keep in mind is that the solar flux in France is about 1,000 watts per square meter if you are mid-summer on a not too day as today. So the max power is about 1 kilowatt per square meter. And if you take into account weather, if you take into account days and nights, you have an average yearly power of about 150 watts per square meters. If you try to understand what these figures mean, it means that if you want to produce the electrical power of France on average over the year, the surface you need is actually 10 to 20% of the surface currently covered with roads. I want to emphasize here that it doesn't mean we should make solar roads. I'm not advocating solar roads here. I'm just talking orders of magnitudes in terms of surfaces. And I'm considering how much surface we need to have the yearly production without considering power stability or anything, just energy balance, because I still think it's a relevant order of magnitude to have in mind. To me, what it really means is that solar raises issues in terms of it's a diffuse source, it's an intermittent source, absolutely, but it represents an energetic manna. It is, strictly speaking, energy falling from the sky. And in the context where we try and think of our energy supplies, I don't see how we could not consider it as a potential energy resource and try to figure out how to handle its drawbacks. So you have, let's say on average, 150 watts coming from the sky. What can you do with this power? Well, essentially you can do 3 things. You can convert it into chemical boundaries, into chemical bonds, and this will give you biomass, for instance, with a photosynthesis process, which has about 1% of power conversion efficiency. You can perform a transformation from solar energy into heat. This is called solar thermal, and it has an efficiency of about 80%. Or you can try and convert this power directly into electricity, and this is what solar photovoltaics aims at. And in the next coming slides, I will be discussing how efficiently can we perform this transformation. So here, I'll just like to take one step towards basic principles to try and explain you how solar cells actually work. So I got quite a few animation on this slide, and I understand that the video is lagging a bit. So I'll try and make sure that we have enough delay. So what happens when you try to convert solar light into electricity? Well, what happens is you have a solar spectrum, that is to say a distribution of photons with different energies. And you try to absorb these photons with a material which is characterized by what is called an energy gap, this EG here. What this energy gap tells you is photons with lower energy than the gap will not be absorbed. So you're losing all this range here of the spectrum, photons with too little energy. And photons above the band gap can be absorbed, and each of these photons will bring an electron from the valence band up here to the conduction band. Now, of course, these electrons will not stay up in the band. It will relax towards the bottom of the band here. And if you absorb many photons, of course, you will accumulate electrons here. And these are the electrons you will want to use to produce electricity. Now, of course, the electrons, if you just leave them alone, they won't stay in the conduction band forever. At some point, they will relax towards the valence band. So you need the material to absorb light, but you also need the material to make sure that these electrons have a long lifetime. Of course, you're not satisfied with the electron just sitting here in the middle of the absorber. You need them to move towards the electric contact, where you can extract them from the absorber and actually have them work inside an electrical load to produce electrical power. So the third key property for solar material is that you need transport of carriers. And then what essentially happens is you use the energy of the carrier as it goes back from the conduction band down to the valence band here. So for each carrier which you extract, you get an energy which is roughly the value of the energy gap. So if I try to wrap this up, what does this picture tell you? It tells you that if the gap is very, very big, then each electron you get will give you a lot of energy. But as the gap is very, very big, you will be absorbing very few photons. So you will have very few electrons. So you will have a very little electrical current. So you're going to have a large voltage, but a low current, and so a low power. If the gap is very, very small, then you are happy because you absorb all the photons, and you're going to have a large intensity. But each of the photons will produce an electron, which will give you very little energy. So you will have very little voltage, so you will have very little power. So you understand here that essentially, if you have a low gap, it won't work. If you have a high gap, it won't work. You need to aim for something in the middle where the value of the gap is well adapted for the solar spectrum. And this is what I show you here on the right-hand picture. I think you see it now. This is the maximum power conversion efficiency which you can get as a function of the gap. And you see that the max power conversion efficiency you can get is about 30%. This is called the Chopelet-Queisser limit. And it works for a gap which is about 1.1 electron volts. This, as you see, comes from the fact that we use one single gap for this conversion scheme. And so it doesn't really depend on the material you're using. The material will tell you if the gap is good or not. But this 30% efficiency is the best efficiency you can get for a single junction scheme. This is also why we're using silicon for solar cells, because silicon has a gap which is close here to the optimal gap for power conversion of solar power. So I think this image here is interesting because it tells you that this 30% max efficiency is a basic limitation for single junction solar cells, and it also tells you which kind of materials we will be looking at when we want to make a solar cell. We need a material with a gap around the electron volt of band gap, and we need this material to satisfy these key functions, which I have discussed when talking about the conversion scheme. So to me, this very simple picture gives you a hand-waving understanding of the material constraints when you want to do solar power conversion. So where are we at today in terms of efficiencies? Well, if I try to put this on scale from 0 to 100%, this here is the 30% efficiency limit coming from the Shockley-Quasar model, which I have just discussed. The best silicon solar cell that we have ever made in a lab is about 27%. So you see that the best cell is close to the maximum theoretical limit. And this here tells you the range which you have for basic research, essentially. Commercial systems which you can buy on market are, let's say, between 19% and 22%. This is what you can buy and put on a roof or in a solar farm. And so the difference between this 20% efficiency and the 27% efficiency is essentially the margin which you have for industrialization. How much can you get from the one single best cell to the industrial production? But of course, we can try and make things more clever than the Shockley-Quasar model, which I have introduced before. One way of doing this is to stack different junctions on top of each other, such that you will have a first cell which is very good for high energy photons and which will leave low energy photons pass by, and these lower energy photons will be collected with the second cell, and then maybe you can use the third cell, and so on and so forth. And today the world record is using 6 cells stacked together, and it reached 47% of power conversion efficiency. Now, this here is a lab proof of concept. It's a cell which is about 20 millimeters squared of size. So of course, the point here is not to make it to market in the next 5 years, but it's to show that we are able to convert a solar spectrum to electricity with a very high efficiency. And if you look for the actual ultimate limit, this is what is being given by thermodynamics, and it's at about 86% of efficiency. So this is trying to put everything together on a line, but actually if you look at what really are the data from PV technologies, this is what it looks like. And so this slide is really here essentially to be a little bit scary and to show you the many different types of solar cells which you can get and the different values for efficiencies. So if you look at this slide, you see over time the power conversion efficiency increasing for different solar cell technologies. Silicon solar cells are the blue line, which are here essentially. So if you follow this blue line, you will get here up to the 27.6% or 27.7%, which is the 27 I mentioned before. You see here the 47% of the absolute best cell stacking together 6 junctions. You might have heard about perovskites if you're interested in solar cells. Perovskites are this line here, which shows a very fast increase in efficiency. But if you try and look here, you will see that most of these cells are below the 30% line, which I highlight here in red, which is the Shockley-Quasar limit. And all cells which are above this line are actually cells using several junctions stacked together, and single junctions are limited to the 30% limit I have mentioned before. So when you talk about solar technologies, what can be a little bit puzzling is you can be talking about any of these lines, and you see that there is a huge jungle of lines. So for this presentation, I will actually focus on one of these lines, which is silicon solar cells. And the reason why I will be talking essentially or exclusively about silicon solar cells is that silicon today represents a little bit more than 97% of the actual market. The remaining few percent are all the other cells which you have seen. So when you talk about solar cell, and if you don't make a more accurate statement, you're really talking about silicon solar cells. So in the rest of this presentation, I will be giving you notions about silicon, because I think as of today, it is the most representative data which you can have when you talk about solar energy. When we talk about silicon, we actually talk about a range of scales, which goes from, let's say, raw silicon, silicon chunks, which looks like this, all the way to silicon modules, that is to say what we call panneaux solaires, solar panels. And in the next coming slides, I will be telling you a little bit more about these different ingredients of solar cells, how to get from one to the other, what do the processes look like, and what are the orders of magnitudes about all this. So I'm getting here somehow to my second part, where I will start giving you orders of magnitudes and notions on the state of the art of current solar cell technologies. When we talk about silicon, as you see in this picture, you actually have two ways of making silicon. You can either make a monocrystalline silicon, which is looking like this wafer here, or a polycrystalline silicon, which are more like this one. I will just give you a few words about these two things here, because I think it's interesting to have a notion of the basic ingredient under or behind a solar cell. So the first step to make a solar cell is to produce wafers, that is to say, these thin pancakes of silicon, which will be the basis for the solar cell. I will not be commenting this whole images. I wanted to have these information inside of the slides for reference, and I will give you the slides afterwards so that you can dive in these figures a little bit more if you are interested. But essentially, the notion is you start with pure silicon, you melt it, you draw one single crystal out of this molten silicon. This one single ingot of silicon is about 2 meters long and about 20, let's say, centimeters, 15 centimeters of diameter. And then you are going to cut this large ingot into wafers. Typically, these wafers are about 160 micrometers thick, and they have a typical surface of 244 centimeters squared. That is to say, about 15 per 15 centimeters in size. And I wanted also to show you this because I think it's quite funny. You have this round ingot, and in this round ingot, you need to cut pieces which you will use to pave a solar panel. So ideally, you would like to have squares. But if you want to cut a square inside a round ingot, of course, you're going to have a lot of losses because you're going to cut all around the remaining pieces, which you see actually here in this scheme. So what is the best way to extract wafers from a round ingot and use this wafer to pave a plane? Well, the best way is actually to cut a little bit the corners of the square, and this is what gives this very typical shape to monocrystalline silicon wafers. And so, if you see a solar panel with this kind of openings here at the corners of the cells, which are being connected together, you know it is monocrystalline silicon solar cells. So this is a trick if you want to recognize the solar panel just looking at it and sound clever. You can say, oh, this one is monocrystalline silicon. Just need to look at the corners. By contrast, if you do a multicrystalline silicon, you don't have one single crystal ingot, but you melt silicon, you cast it into an ingot, so you can give this ingot a shape which is much easier to cut. And so at the end of the day, the wafers which you have are perfect squares, and it's much easier to pave the plane. So this is how you get from the raw material to wafers. then you need to turn this wafer into a solar cell. So you need the device which you will be producing at the end of the day to have the properties which I have mentioned before. You need it to absorb light, you need it to keep carriers alive long enough, you need it to be able to transport these carriers, and you need the carriers to go selectively in one direction and not in the other if you want to produce a net current. This is what all the steps which are presented on this picture are here for. So, for instance, you will start by texturing the wafer. So you will, you don't want the wafer to be perfectly flat. You want it to have a nano-textured surface because you want the light, once inside the material, not to escape too easily. You want to trap light inside the material, and in this way you can reduce the amount of material you need to absorb all the light. This is called light trapping. You also want the light to get inside the material and not to be reflected towards where it came from. So you will add some anti-reflection coating. This is the silicon nitride here, which is represented in blue. To produce selectivity, you need to dope the material. So you will add some phosphorus to the cell. This is the red layer, which is pictured here, to produce the selectivity, which I have mentioned before. So if you look at these steps here, you can try and identify how each of the key functions, which I have introduced in the basic Shotler quasar model, are actually implemented in the industrial process. What you get at the end of the day is something which looks like this. So this here is the most standard silicon solar cell which you can find on market today. The thick layer here, that's the wafer itself. This is the 160 micrometer of silicon, which is initially p-doped and that you use at the early stages. The p-doping comes from very few boron impurities inside this wafer. The n-doping, which is here, the n-silicon, comes from diffusion of phosphorus, and it is what allows the selectivity to make sure that current will flow in one direction only and that you can produce a net current. Silicon oxide, which is here and there, allows passivation. So it is here to make sure that carriers will remain in the conduction band long enough for you to have time to extract them. The arc, which is written here, this is anti-reflection coating. It's to make sure that light is well absorbed inside the material, and it's typically made with silicon nitride. Then, of course, you need metals to produce electrical contacts. Usually you use aluminum at the back side of the cell, and you use silver on the front side of the cell. To my knowledge, silver is actually the most critical material when it comes to making a silicon solar cell. But of course, you would have heard in my shopping list for a good solar cell that there are no rare earth involved here. You don't have erbium, you don't have ytterbium or neodymium or whatever these fancy materials which we're very worried about. None of them actually appear in silicon solar cells. Other technologies might use some amount of rare earth or of more critical materials. You have gallium in some cells, you've got indium in some cells, and it is a relevant discussion to know whether using these materials makes sense or if we should just refuse to use these materials whatsoever. But in any case, these questions don't apply directly to silicon solar cells, which once again are about 97% of market today. Finally, once you have cells, what you are going to do is you're going to take these cells together. You're going to put 60 or 72 of them connected in series and parallel, and you're going to encapsulate these in glass. You're going to frame it and sell it as a solar module, which you can actually sell to customers. So now I'm really going towards the second part of this talk, and I will give you market notions of PV modules. And what I really like to do in this discussion is two things, is to show you how these things evolve and how they evolve fast. And this is to give you the notion that if you want to think about solar, you really need to update your figures on a regular basis. And I will try also to give you a reading grid and to draw your attention on some, how to say, subtleties in the different definitions, which I think are required to understand what the figures really mean. Because there are many different figures, they don't all address the same things, and I think it is key to understand the meaning of these figures of merit. So I will start by talking about costs of solar modules. So when I talk about modules for now, what I'm really talking about is what it costs to produce the module out of the supply chain. So you see the unit here, I'm talking in dollars per watt. What it means is I'm producing a module, I'm illuminating it in standard conditions, that is to say the AM 1.5 spectrum, 1000 watts per square meter at ambient temperature. I look at how many watts this module is able to produce from this illumination. I calculate how much producing the model costs, and I make the ratio between these two quantities. So it doesn't tell me anything about integration, of course. It doesn't tell me anything about lifetime of the module. It doesn't tell me if the module often works at its nominal power or not. But the interest of this figure of merit is that as it's just out of the line, it allows me to compare different modules in the same conditions. And so if I want to have a notion of how is the industry itself performing, then this here is the good indicator, because it tells me what happens just outside of the gate of the industry. What you need to see in this graph is the spectacular shrinking of costs. Essentially, to produce a module which would give you 1 watt, it would cost you $100 in about 40 years ago. It costs you 20 cents now. So, of course, we can talk about the additional costs, but this really, to me, shows the spectacular improvement of the industry and how costs have been driven down spectacularly. And this really highlights this notion that if you want to have notions about the cost of solar cells, you really need to look at the figures just before you talk. Because even 5 years ago, costs were maybe 2 or 3 times more expensive than what it is now. And this shrinking of costs really gives a notion of the dynamics of the sector. This here is the cost that the economical cost as reported by the International Roadmap for Photovoltaics, and all the references here are in the last slide of the presentation, so you can dive into these reports if you want more details. So this 20 cents per watt, where do they come from? Well, you see that it's about 1/3 for wafers themselves. It's about, okay, let's say globally a little bit less than 1/3 for turning a wafer into a cell, and it's about 1/3 for turning cells into modules. And actually, the largest part today is the materials for modules, that is to say, the layer of glass and the aluminum frame, which you're going to use to make modules. Today, this is the most expensive part for a solar panel. There again, this is the cost outside the industry gate. So we need to compare this cost to what is called the installed cost. Installed cost is what it's going to cost you to put this solar panel somewhere, either on your rooftop or in a solar farm. So in addition to the module cost, so you see that the module here now is just a fraction of this cost. It's about, depending on how you install the module, it's 10 to 30% of the cost. On top of this, you need to account for electronics, for hardware, that is to say mounting racks and everything. You need to pay the installation, and you need to pay taxes, you need to pay capital, you need to pay land acquisition or renting, and so on. So at the end of the day, the cost of the module is about 10 to 30% of the cost of the solar panel installed somewhere. So yeah, this is the additional hardware which you need to take into account. So racks, inverters, wiring, and the manpower to install all this. Then the next step, of course, is to consider not a cost per watts, but to consider a cost per energy. And this would be the levelized cost of electricity, the LCOE, which accounts not only the installed cost, but also how well is the device going to perform. It's not performing always at its nominal power, in particular at night when it's not performing at all. You need to pay maintenance. You need to account for degradation. And so here is another order of magnitude, which I think is good to have in mind. Today, a silicon solar panel has a typical efficiency decrease, which is about 0.5 to 1% of its nominal power per year. What it tells you is that in 30 years, if you buy a 20% panel, it will go from 20% to about 17 or 16% of power conversion efficiency. So even after 30 years, it's still performing actually better than panels you could buy 10 years ago. So the typical lifetime of panels is about 25 to 30 years at least. And I want also to emphasize that this levelized cost of electricity, that is to say really what is the cost of producing electricity, is about 1/3 itself of the actual electricity bills which you pay at the end of the day, which has to include also grid integration and taxes. And I've got the 1/3 ratio from the analysis of Jacques Percevoix. So you see that at the end of the day, the cost of the cells themselves are just a very small fraction of the cost of electricity which you can pay at the socket. And to me, what these numbers show is how it is important today to aim for higher efficiencies, because with higher efficiencies, even if you increase a little bit the cost of the cell, you can decrease the overall cost of electricity. But I'll get back to this towards the end of this presentation. So this here is just to compare a few costs of electricity. You will have this in the slides. And this here is another very important notion related to cost, which is the notion of energy cost, or more generally, the environmental costs of solar panels. There again, you can think of many parameters to calculate these things. The most basic frame to calculate this is to estimate the cost of the solar module. And so these are the figures which I give you here. Today, it is estimated that a solar module used in Europe will produce as much power as it required in the first place to extract, melt, and process cells. It will pay back this energy in about 1 year of time usage. So the module will be used for 25 to 30 years, and within a year, it will pay back the energy it cost to produce the module. And I really want to emphasize here, I'm only talking about the module. I'm not including here what it costs to add power electronics on top of this, what it costs to add storage if you need storage, what it costs to perform grid integration, because all these things here will come on top of this year, which I'm mentioning, but it will really depend on how you actually perform things. So I don't claim that this 1 year timescale is the definitive answer to all the questions that we are asking. I say it's the most basic unit on which we can all agree, and then we can discuss what are the additional things which need to be added on top of this. This slide here is about the how solar panels are actually being installed in the world. So it is actually quite spectacular that over the last 20 years, you can actually fit an exponential in there. And we all know how exponential can't last forever. And I'm not even sure that we should hope that exponential ever lasts forever. But over the last 20 years, the solar installed capacity has increased by about 42% per year, every year. I told you that I wanted to raise your attention on words which I used when we talk about solar. When we talk about installed capacity, what we talk about is what is the maximum power that panels worldwide would produce if they were all illuminated in the optimal conditions at the same time. So the installed capacity is, let's say, if you take one installation, it can be the power which is produced once during the year, the 21st of June at midday, if everything works fine. But if you want to know what is the real production, you need to take into account what is called the load factor. This is what gets you from the 1000 watt per square meters as the maximum illumination to the 150 watt per square meters as the yearly average, which I have mentioned before. This is where you recover this 15% of typical load factor for PV installations. So there again, when we talk about having 500 gigawatts of world capacity in solar, we need to be aware of what it really means. How are these panels being installed? Well, in 2018, China had installed about half of the 100 gigawatts which were installed this year. And if you look at the actual total capacities since the dawn of time to the end of 2018, China again has the largest park of power of solar production. Europe is second, Germany being a huge chunk of this 23%, and India is progressively drawing a larger and larger part of the total world capacity. How are these panels produced or installed? You see that it's about, let's say, a large third of the installations are rooftop installations, about 2/3 of the installations, or let's say, yeah, between 2/3 and a big half are power plants, so solar farms, and a very, very small fractions are floating PV or building integrated PV. But this here for now is quite negligible. And about 100%, maybe 99% of these installations are connected to the grid. Very few of them are standalone installations. Last slide about the state of the art of the market. This tells you where solar panels are being produced. And what is spectacular in this graph is to see that before 2005, the Chinese production was quite limited. Most of the production was coming from Europe and Japan and a little bit from the US. Between 2005 and 2012, say, about 70% of the production moved to China. So China really got the market of solar PV within 7 years. One of the key drivers was that they could perform solar modules at a much cheaper cost than anywhere else. But I have also discussed here how the cost of modules at the end of the day will be just a small fraction of the cost of electricity. To conclude this presentation and the last 5 minutes which I have, I would like to just flash 4 of the challenges which I think need to be tackled now. I think these challenges are not limiting yet, but I think that if they're not addressed, they will become bottleneck for future development of solar power. I had it in the slides, but I didn't have time to comment it. today solar power is about 3% of the world electricity. So today it is significant, but it's clearly not the main actor of electricity in the world. If we want, or if we think that these 3% will increase, then we need to prepare now for issues which will arise when we will reach 5, 10, 15% of electricity production if we manage to reach these levels. The first challenges I want to raise are related to the industry itself. Today, we're able to produce about 100 gigawatts of additional capacity per year. How can we scale this up? And how can we scale this up in a meaningful way, both from economical, ecological, and social perspectives? And I just here bring the question of this scaling up. It can come from different processes. How can we get from painting technologies, which is today standard? We make short, small cells and we put them side by side until we have a panel. Can we get to coating technologies to be able to cover large surfaces in an easier way? How can we include from the early stages of solar panels the end of life of solar panels? Today, there is one plant in the world which is dedicated to the recycling of solar panels, which makes sense because solar panels have 20 to 25 to 30 years of lifetime. 25 years ago, the amount of solar panels which were installed was quite limited. So we are now getting the first wave of solar panels to recycle. And so this industry is powering up. But at the same time, solar panels at the time were not made to be easily recyclable. So we can recycle easily the outer layer, the window, which is being used to encapsulate. We can recycle easily the frame, and window and frame is the largest amount of mass in a solar panel. But today, the options for recycling the solar cell, which is the technology part, into a new solar cell are quite limited. Can we think of ways of conceiving, of designing these cells to help recycling 25 years after the cell is actually being produced? The second challenge which I want to raise is a little bit less energy related, but it is market related. And it's to think of developing innovative applications for solar panels. I really, really don't claim that these applications will change the face of the energy sector in general, but they can. They have two interesting options to my mind. The first one is it can help the field moving forward in terms of innovation and of driving forces, and it can help solar energy getting closer to citizens and customers. And we know that having people involved with energy issues makes them raises the awareness towards energy in general, and we need this awareness to be risen. The third challenge which I will mention is the one which I am focusing my research on more specifically, and it's aiming towards very, very high efficiencies. We have seen how single junctions are limited to 30%. We have seen that we know how to overcome this limit, for instance, playing with the architecture of the cell, stacking two cells together, one which will be good for high energy photons, one which will handle low energy photons, and how doing this we can overcome this 30% limit. There are other things which can be done, playing with light, playing with carriers themselves. And to me, these questions, there again, have at least two interests. First, I am convinced that increasing efficiencies is key to reduce costs at the end of the day. And second, this is basic research. And so when you perform basic research, you know what you're looking for. You don't know exactly what you're going to find. And asking these questions requires to go back to basic notions of energy conversion in semiconductors. And this can bring results not only to high energy issues, but more generally to the solar sector, and more generally actually to solid state physics. And finally, of course, we cannot avoid mentioning grid integration. Essentially today, grid integration is not the limiting factor for solar energy, because solar energy is still limited at 3% in most electricity mixes. But if we want grid integration not to become a bottleneck, we need to investigate now what can be done about this. And there are things to be done regarding production, and especially thinking about using several energy vectors at the same time. How can we, on location, on production sites, transform solar energy into chemical, or solar energy into thermal, to maybe help integration? There are things to be thought about the grid itself. How can grid be adapted to help integrating larger shares of intermittent sources? And there are things to be thought about consumptions. What can we change in our own relation to electricity? If we change drastically the way electricity is being produced, then of course the use of electricity which we're going to have cannot remain exactly the same. And so there are things to be adapted on our usages as well, if we believe that intermittent renewable energies are to play a key role in the energy sector worldwide. I'm concluding here this presentation. So this is a graphical wrap-up of what we have discussed over the last 50 minutes. First part was about orders of magnitudes, and essentially highlighting this 30% limit, the Shockley-Quasar model, which tells you at the same time how much you can think, how much you can dream to have with a single junction. Why are we using the materials we're actually using, and what can we try and think to overcome this limit? The second part was really about state of the art of the PV sector in terms of costs, in the economy and ecological perspectives, and how these things evolve fast with time. And the last thing is to say that some years ago, people said that PV would never become more than the thickness of the line, that it would never become a significant actor in the electricity, in the power sector, where I think today's situation shows that it's not true. PV can actually produce power in a significant way, but it doesn't mean that all problems are solved. There are still issues and challenges along the way which have to be tackled now if we don't want them to become bottlenecks in the future. Thank you very much. That is essentially what I wanted to share with you on these questions.
Many thanks, Daniel, for this clear talk. So we have some questions in the chat. So we will start with the technique questions. So Jean-Yves, if you want, you can ask yours. Jean-Yves? I can ask his question maybe. Jean-Yves is, yeah. Okay, so I will ask Jean-Yves' question. So, how resistant to degradation are solar panels? Rain, acid or not, wind, dust, bird droppings, shock, hail, freezing?
Yeah. So most of the environmental degradation are what is being included in the figures which I have given you here. So when I say that degradation is about 1% per year, and so efficiency drops from 20% to 16, 17%, this includes rain, acid or not. It includes wind, it includes freezing and hail. And remarkably, it is quite similar figures in different conditions. Actually, when there is a spectacular image if you look at solar panels which are taken down from satellites. And these solar panels are just wrecked and shrinks with shrapnels from impacts of meteorites and things. And they still work up to 10% of efficiency. So silicon solar cells are pretty robust. And actually, I will include in the slides a compendium study on degradation, where you can see these figures estimated from desert environment, tropical environment, temperate environment, and snow environment. And in all cases, it is about the same order of magnitude. Dusts and bird droppings, these are related to maintenance issues. And I have little figures on this. I think it really depends, in this case, in which conditions you're operating the cell. Of course, if you operate it in a very dusty environment, I expect that you need to clean the panels on a regular basis, because if no light gets in, no electrons will go out.
Okay, so he has another technical question. How much is lost when converting DC current to AC current that can be injected in the energy grid?
Good question. I don't have this order of magnitude top of my head. I tend to believe, but there again, this would require more checks that onduleur. What do you say onduleur in English? AC/DC converters. I used to know this word. Whatever. Do have a good efficiency, and they're designed for this. So I don't believe that this here is a significant loss when it comes to energy conversion.
Okay. So then we have a question from Jean-Claude Dutet. Jean-Claude, do you?
Yes, you hear me?
Yes.
Yes. First, thank you, Daniel, for this very interesting talk. I will use many information that you provide for my course on the energy at the university. My question was on the still, what are the main risks and damage on the environment during production or recycling? Is it the silicon chemistry, or there is other pollution on the environment?
It's a very good question. First, thank you very much for the feedback. It's of course a very good question. So I am not expert in the industry process directly. I'm actually working on it right now, but I don't have definitive answers on this. So what I will give you here is my understanding, but it would be worth checking it against other sources. And I would recommend reading this report here, where they go more into the details of the different chemicals and physical treatments of the processes. To my understanding, clearly what is the most energy consuming bit is producing the wafer, because you need to melt the silicon to purify it, and to purify it to very high purity. And this here is the most demanding part. Now, is it also the most impacting in terms of chemicals? I don't know. And I'd rather not say something completely wrong here. So 2 answers. First, energy-wise, it is really this step here which is most demanding. And for more details regarding chemistry pollution, I guess the good reference is this report here. The link will be provided in the slides.
Okay, thank you.
Okay, so we have two questions about the energy mix. So François-Marie, if you can ask yours.
Yeah, thank you, Daniel. Thank you so much. And but you know that the main problem I see with the development of solar PV in countries like France is actually the fact that the solar panel produce mostly during the summer and not so much during the winter. I mean, I think that there is a factor of 5 between the mean production in June compared to what it is in January. And on the other hand, the demand for electricity is about twice as large in winter than it is in summer. And so this full decoupling between the production and the demand makes me believe that in the future, if we develop the solar panel, we will develop other means, and these other means will most likely be the gas. And I'm afraid that it will, in fact, increase the emission of CO2 in France. So, do you have any comment about that?
Yes, I think it's a very, very legitimate concern, and I think that if we just let things be, and if we just hope that markets will drive the way, it will clearly not go towards directions that we are calling in our wishes. So we need to be concerned about how things are actually being implemented, and to make sure that the claims which are brought up when something is being done makes sense and is relevant with regards to what is actually being performed. I would nevertheless answer this question by going to this figure again, and it's to say that even if I totally agree that we really need to be careful on how things are done and not pretend that putting solar panels everywhere will solve all the issues. On the other hand, we have 10,000 times the amount of energy which we use coming down out of the sky. And we cannot disregard this. We need to find clever ways of using this energy. And to me, it will come with improving our production management. This can include storage, this can include flexibility, this can include many things. It will come with adapting our consumptions. We cannot change a fully dispatchable source with an intermittent source and pretend that we're going to have the same service being brought without huge adaptation costs. This is, I think, clear. And I don't know right now what it will take and what will be the actual, what can we really expect at the end of the day. But my conviction is that solar will play a key role in the energy landscape in the future, and we need to prepare this and to make sure that the claims which we make are honest and meaningful. And I hope it kind of answers the question.
So Paul has also a question about the energy mix. Paul?
Yes. Do you hear me?
Yes.
Yes.
Okay. So thank you again for the very nice and very easy to understand talk. Very well explained. Yes, my question was not exactly the same as the question from François-Marie, but really similar. It was about also about this question of intermittency, and I've heard some people say that if you use intermittent sources of energy like wind and solar, and if you still want to have to meet the same demand as you are used to meet with other sources of energy, and so that you have to mix intermittent sources with constant sources like coal or nuclear or gas. And some people say that once you mix those two, you have the constant sources are not so efficient because you have to turn them on and off. So in the end, you might not even get such a big advantage of using solar and wind versus using just coal or nuclear. So yeah, there are many, but actually I think you almost already answered that question just before. So if I get a bit more personal, my personal concern is that we are trying to work for the energy transition, and we see that there are many challenges if we try to make the transition from fossil energy to renewable energy. And my fear is that instead of making energy transition, we're going to make energy accumulation, so that we're just So what do you think about that?
There again, I totally understand this concern, and this is where I really believe that solar or wind or actually any other form of energy are ultimately tools, and that it really depends on what we decide to do with these tools. But on the other hand, you can't pretend that a tool is able to do something it cannot. You can have a very good hammer, it won't help you to saw a log, for instance. So what I really wanted to do with this presentation was to try and give you what I hope to be a honest perspective on solar and what it really does today and what is coming next. I think from what I hear in public debates, you've got the two ends of the spectrum. You've got people claiming that you just need to put solar panels everywhere and the problem will be solved. I don't believe this is true. And you also have people claiming that solar energy or wind energy are utterly useless because they can't handle an electrical system. You can't replace current sources just by these things and hope that everything's going to work. So it is useless. And I think that this conclusion is equally flawed. Of course, if you want to use renewable sources, wind and solar, which are intermittent, to reduce the amount of fossil electricity, you need to make a proper balance and to estimate how much can you reduce the use of thermal plants, and if you lose efficiency, how much more will we have produced with respect to what you would have otherwise. Nevertheless, and that's where I bring out this slide to make sure of the figures. 650 terawatt hour of solar electricity being produced worldwide in 2018. In the extreme vast majority of countries, this electricity is being produced with, the rest of the electricity is being produced with thermal plants running on fossil fuels. So I'm quite confident that this production here actually contributed to not emitting some fossil fuels. What is the exact ratio? Is it 1-to-1? I don't know, and I don't think so. And I really emphasize here that I'm talking worldwide and not specifically of France, where electricity has a very low carbon intensity already. But I think anyway that the problem has to be thought worldwide. So to try and wrap it up and answer also the personal comments which you raised and which I really share, I also believe that if we're not careful and if we're not aware of the pitfalls, and if we don't fight against them, then there is no reason why this energy transition would be different from every previous energy transitions where energy sources just stacked on top of each other. But just because it happened like this in the past doesn't mean that it has to happen like this again now. And I also believe that it is our role to share these concerns and to share it outside the labs. And I make this presentation, for instance, or a lighter version of this presentation to groups of citizens which want to get involved in installing solar panels in their cities, for instance. And what I really try to pass as a message is this balance that you need to be to know what are the actual performances and dynamics and how the PV sector is moving forward. And you also need to be aware that it's not a miracle solution that will just solve everything. And I think that this message is really important to convey.
Okay, so
Thank you very much.
we have a question from Gilles. I just unmute him. It's okay, Gilles. You can...
Okay, thank you, Nana. You hear me?
Yes.
Yes.
Okay, so I have several comments and a question too. The comments are first, I'm very glad because you show not only the theoretical threshold for the efficiency of solar energy, but also to go to the market and the technological problems. I think it's quite a good spectrum. Another thing is that I agree with Paul and you that till now, I think, because I think most people were not aware about it, the energy has always been cumulative.
Mm-hmm.
I think the solar energy may be an energy that is more not so centralized. And as you said, people are interested and can do something, and they will be more and more aware. So maybe next transition will be a real transition. And my question is a really naive question, but I look to the demographic curves for the 2050 that I think are more or less reasonable. So the question is that, do you think it is possible in the next 25 years to transfer technology, and especially solar technology, to a large area of Africa that are not intermittent in terms of sun except for night and days, and that will be able to sustain the increase of amount of energy? And isn't this a very good field for showing that in optimized condition we can answer to the demand, because there will be a demographic demand, and also to change from coal to solar energy? Because you didn't tell us really what we could expect, I mean, regionally and globally, for the photovoltaic in, let's say, for two.
So the end of the question was a little bit cut, but I think I got it so far. Did you hear me, or was it my network that jumped?
Okay. Should I begin again?
I heard the last part of the question. Do you hear me as well?
Yeah, I hear you now again.
So I did show indeed really upcoming trends. I presented you past trends up to today, and I didn't say what I expect the next steps to be. One of the reasons is that predictions are very hard, especially when they deal about future, don't they? And I didn't really devote enough work so far to reading and to evaluating prospects to have a relevant opinion on the matter. And I just here show again the slide with the International Energy Agency forecasts to show how easily it is to get it completely wrong. So I won't be able to answer this point in a technical way, in the sense that I don't have a clear image on what are the results of these estimations and how reliable they are. What I can try and answer, though, is the question of, or at least I can share my opinion, to be more accurate, on this question of can we move the solar industry, and in particular can we have a production line or production lines installed in Africa in a way that people would be producing the panels they will be using, and not necessarily depend on technologies which are brought to them in a new kind of new colonialist way. I believe so. And on the other hand, we see with Europe how difficult it is to make things move forward. We have discussed how modules, the module production lines essentially all moved to China within 7 years, because at this point China was able to produce modules at a cheaper cost than anyone else. Yet today we know that the cost of module is a very, very small fraction of the cost of the installed costs, which itself is a fraction of the levelized cost of electricity, which itself is a fraction of the cost that the consumers actually pays. So my understanding is that it would make sense to say, for strategical, political, and social reason, we want to have more solar panels production in Europe. Even though they are a little bit more expensive, at the end of the day, it won't change much for the cost of electricity for the consumer. So we're totally fine with paying a little bit more to have this production line here in Europe. And I would pretend, of course, that it's the same reasoning which you can have anywhere in the world, and especially in Africa. But to me, this takes a political stance, because if you only follow market trends, then you will put the power plants in locations where modules are a fraction of cents per watt cheaper, and where it is easier to get capital for building up these production lines, and you're not driving things in the direction you like. So to try and wrap it up, yes, I think it is absolutely relevant. Yes, I think it is doable. And there again, to me, one of the key issues will be not to let markets pretend that they drive things along the best possible directions.
Daniel, I also have a question. All the PV panels don't emit the same amount of carbon, so are there debates to tax the most emitting ones, or make attractive the other ones?
So there again, I really focused here on silicon, and the numbers which you can have and the figures which you can have can be quite different if you consider other technologies. For instance, I gave you this 25 to 30 year lifetime for silicon solar cells. And lifetime, of course, is critical when it comes to life cycle analysis, which will impact both CO2 emissions, pollutions, or economical costs at the end of the day. If you look at perovskite solar cells, today the lifetime of a perovskite solar cell is about a few months, which is also the reason why it didn't really made it to market yet. So of course things will be completely different. On the other hand, perovskites don't need high temperature processes. They are processed at low temperatures. On the other hand, they use lead. So all of these questions, of course, needs to be balanced depending on which technology you are really talking about. I don't know to which extent there are considerations for taxing or paying differently different technologies based on their environmental impacts, and how would you weight the different type of impacts which you can be considering. To my understanding, I would believe that silicon solar cells are maybe the most CO2 intensive solar panels, because they require high temperature processing, and because of silicon chemistry, where you need to extract this, you need to break the silicon oxide connection, and so you will do this by oxidizing carbon, and so you will emit at this stage carbon dioxide, which is why solar the intensity of solar power is estimated to something between, let's say, 30 and 50 grams of CO2 per kilowatt hour. And I would believe if you need to keep in mind one figure. So first, this figure is the one which comes from the previous assessment report from the IPCC. And I think these are quite outdated figures right now. So I don't know which faith to have in the last digit of this number, but the order of magnitude, of course, makes sense. And I would believe that this order of magnitude is being estimated here for silicon, and that silicon will give you an upper bound for the other sectors, if we talk only about carbon dioxide emission.
Actually, I was more thinking about the energy mix of the country producing the PV.
Oh, in this way.
Yeah, but I don't know if it's
no. To my knowledge, this is not being considered now, and of course it is a real problem. Well, it is a real problem if you want to install solar panels for reducing CO2 emissions. I mean, you can decide to install solar panels for other possible reasons. But of course, if your aim is CO2 reduction, then you need to estimate this specifically. And from what I see, it's not made very often.
Many thanks, Daniel. So we have another question from our colleague Yeling. So Yeling, can you take the floor?
Yeah, thanks for the presentation. It's very clear. I have a question about the technology of concentrated solar power. So
yep.
The market share of this technology is still very low. So what's the main challenge of this technology in the market? And this technology has some sort of storage capacity, so which is more flexible. Why the market share is still very low? That's mainly because due to the high cost of this technology, or still some technology issues. And what's the future of this technology?
So there is indeed I presented you here the most straightforward solar panels. You take something, you put it under sunlight, and it produces electricity. You actually have a range of complementary or additional technologies, and in particular CPV, concentrated solar photovoltaics. And there again, you have different ways of doing things. I guess the one you have in mind is the one which is essentially, wait, I might have presented it here, where you have a tower somewhere in the middle, you have mirrors all around, you focus light onto the tower, and you produce large amount of heats, which you can then use to drive a turbine and produce electricity, or you can try and store these heats if you want to use it later on. I don't have a definitive answer to your question as of why is this technology not much more developed. I think I can make some hypothesis here. I would say several things. First, these technologies here are much more demanding in terms of installation than what you can have with solar panels. You can't make such an installation on your own rooftop, for instance. And rooftop does represent about a third of installed PV over the last years. don't know exactly what is the actual conversion efficiency which you can get from these installations. I don't know what is the lifetime of these installations, and I don't know what is at the end of the day, the cost per watt which you get from these installations. So all these things would need to be looked at if you want to have an answer to your question. The last thing I would believe is that as of today, storing electricity or storing energy and making electricity later at night has not been a critical factor for promoting an electricity production plant. You don't have sanction for not producing electricity at night, and you don't earn more money for producing electricity at night in the current scheme of production, let's say, roughly. So I think that this advantage which you have for storage when you look at thermal conversion actually gives you little advantage on markets today. They might give you more advantages in the future if we get to a point where we consider that storage becomes critical for the grid. But as of today, it is not yet. And so I would believe this is also why this feature does not provide a clear advantage to these technologies. But there again, these are my understanding, not my expertise.
Okay, so thank you very much. I guess we don't have questions anymore. So thank you very much, Daniel. Maybe I give the floor to Gilles for the Gilles, the mic is on.
I hope you hear me. Thanks a lot, Daniel. I think it was really a very pedagogic talk, and I think this is a key issue for many of us when we discuss about climate changes. There are so many questions about trajectory, energy, what we can do. I think it's quite good if we can share your slides. Jean-Claude already told that he will use them for his course on energy, but I'm quite sure that many people in the audience would be happy to share the slides and to get the order of magnitude in this discussion. Thank you, Daniel.
Great pleasure. Thank you again for the invitation, and hope to see you soon live.
Okay.
Bye-bye. Thank you very much.
Bye.
Bye-bye.